All right, the last reaction we're going to cover for chapter 20 seems to not really fit into the chapter that well, so I wanted to have its own separate day. This is called the Baeyer-Villiger oxidation, and I'll show you the overall reaction, and then we'll get into the mechanism. So if you have a ketone or an aldehyde, you can react it with a peroxy acid. And if you remember, a peroxy acid like MCPBA is basically a carboxylic acid with an extra oxygen shoved in. And when you do this, you'll end up getting an inserted oxygen. And sometimes people will ask me, well, which side of the ketone will it get installed into? And there's actually a very firm set of rules you have to follow in determining which side the oxygen gets delivered to. So if you start with an aldehyde, you can convert it to a carboxylic acid directly. Before, what we had to do was we had to reduce our aldehyde to an alcohol and then oxidize it to a carboxylic acid using a chromium-based reagent. In this case, we can avoid chromium and just use a peroxy acid, and it works really nicely. If you go with a ketone, you're going to form an ester, but like I said, the position of the oxygen depends on those R groups. So let's take a look at the mechanism. And this mechanism is a little bit complicated. So the first step involves this peroxy acid. And this oxygen on the end is nucleophilic and can attack the ketone and kick up electrons, but this is reversible. Let me clean this up a bit. Then we've got this intermediate. At this step, the carbonyl from the peroxy acid is going to steal the proton. It's actually close enough to do so intramolecularly. And this gets us set up for the oxygen insertion. In the next step, what you're going to do is you're going to take one of these entire alkyl groups and you're going to shuttle it over to the oxygen. And then this bond is going to hop over here and you're going to kick up electrons to the carbonyl oxygen. Additionally, during this step, you can show an arrow coming down from the negative charge on the oxygen and form a carbonyl bond. So there's a ton of arrows here, 4 arrows. We normally don't have 4 arrows in one step. This is kind of the weird exception. So when you do this, you've now made an ester. And then if we follow our other half, we've now made a carboxylic acid. So this is our carboxylic acid byproduct. The thing that confuses people is really this entire group is migrating over to the oxygen. So it's basically called an alkyl shift or an alkyl migration, depending on who you ask. There are some groups that have a higher tendency of migrating than others, and so the general order for these shifts is hydrogens really like to migrate, which is why with the aldehyde you don't end up with an ester, you end up with a carboxylic acid, followed by tertiary carbons, followed by secondary carbons, followed by a phenyl group, followed by a primary group, followed by a methyl group. So the general rule of thumb I follow is hydrogen's pretty obvious. You form a carboxylic acid. And then tertiary, secondary makes sense, right? They're more stabilized if they move. Phenyl groups also stabilize from resonance. And then last but not least, you've got primary and methyl. This phenyl group one's a little hard to remember because it lies kind of in the middle. So it's less likely to migrate than a secondary carbon. Does that make sense? So let's take a look at some common examples of these reactions. Actually, sorry, I'm going to do a 5-membered ring. Oh, sorry, I forgot my carbon. RCO3H. If you do this, you can go from a ketone to a new functional group called a lactone. Lactones are really common in medicinal chemistry. They're found in a lot of natural products. And then the cool thing with this is you can even reduce your ester and go all the way to a diol, right? So if you want, theoretically, you could treat this with LAH. And what product would you get if you treated this with LAH? So we'll do LAH followed by water.
You break the ring, you have two carboxylic or two alcohols on the other end.
Yeah, exactly. So 1, 2, 3, 4, 5. Have an alcohol here and an alcohol here. So you can functionalize this. You can add Grignards into your ester and ring open it too. So this basically is a nice way of converting a ketone to an ester. Like I previously mentioned, you can also, do something like this, where we can avoid the use of toxic chromium reagents. And we can go straight to a carboxylic acid in one relatively clean and easy step. It's a lot easier. All right, let's check one more reaction. This one's a little bit trickier. What product would we get out here? So we've got two options. We could have the oxygen delivered on the left-hand side, or we could have it on the right-hand side. Which one's more likely? The left-hand side, right? We just said that secondary carbons, like this one over here, are more likely to migrate and be attached to the oxygen than the primary carbon.
It's not tertiary. Or do we not count those carbons?
Well, when it's moving, it's a secondary, right?
Okay.
So you can move a tertiary carbon like a tert-butyl group, and that's even the best example. So in this case, this one would be the only product. Make sense? It's the last reaction for chapter 20, believe it or not. So let's take a look at the review of reactions, and then we'll get into just more practice activities. So at the end of the chapter, he has this giant map. A lot of reactions, right? It seems super overwhelming. But what I really recommend doing is writing this out a few times. And then if you want to test yourself, I've got this fill in the blank one where basically I just erased everything. Go through and double check that you know all of the reagents. And then for the mechanisms too, make sure you're comfortable going both forwards and backwards for the reversible ones. Okay, so we've got this review of reactions. Synthetically, we've got a lot to deal with now. So the first thing I do when planning my synthesis is I look for a change in my carbon skeleton. We've always been doing that, right? And then we, after that, determine if the functional group changed. Those are the two most important things you need to address when planning your synthesis. Oftentimes people forget to count carbons, and that leads to problems. Count your carbons first. In this chapter, we did CC bond forming reactions. So for example, if you've got a ketone, you can add in a Grignard reagent, you can add in cyanide, you can use a Villiger reagent, and then we said if you do the cyanohydrogen formation, you can even functionalize that further to a carboxylic acid or an amide. And we also covered some bond-breaking reactions like the Baeyer-Villiger oxidation. And then down here we've got these CO bond-breaking reactions where we can take a carbonyl and basically replace it with 2 hydrogens. And we've got 3 routes. We've got the top one, which is a Clemmensen reduction. Pitfall with that, we said, is it only works well with aryl ketones, meaning there's a phenyl group on one of those R positions. And then the next one is our Raney nickel reduction. This works really well. It's one of the most gentle conditions. However, it is kind of stinky, so that's something to be aware of. And then the last one, we've got the Wolff-Kishner reduction, which also works really well. It's nice and green. However, it does have strong base in there, so it doesn't work well if you're dealing with that, or with base-sensitive functional groups. So I know some of you have your reaction maps from last quarter. Essentially, all this reaction did was take ketones and aldehydes, and now you've got this giant new tree branching off of that. So it's a good idea to review your reaction map and then maybe add in some new arrows coming off of your aldehydes and ketones. So for the remainder of the time today, you've got 2 options. You can work on the synthesis worksheet with your partner or table group, or you can do the practice problems from the book. And then what I'll do is I'll post the key later tonight in the course notebook so you can take a look at your answers. Make sure that you spend some time going through synthesis in particular, because I know a lot of people forgot second term reactions. It's a good idea to review those.